Hello friends, welcome back to my channel Physicist Buddhist. So like I mentioned in my earlier short introduction that in this lecture I will be talking about another classic textbook of quantum mechanics. It's Quantum Mechanics by Albert Messier. I hope you can see the title. Okay, so you can see this is a very big book, pretty thick because it's 2 volumes bound in one. So Albert Messier was a French physicist who published this book in French in 1958, and because it was such a good book, so there was a demand for that in English language, so they published a translated version in 1963. So this is uh, this is a book for students, actually. Let me say this way: so if you want to learn quantum mechanics, if you have watched my earlier channels where I did a review of quantum mechanics by Leonard Schiff and quantum mechanics by David Bohm. So this book belongs in the same category. So Messier talks about, he starts from the very basics. So he starts with the Heisenberg's uncertainty principle and he builds up from there, and he describes what are the quantum of the dynamical variables in quantum mechanics, how the position and momentum become operators, and by Heisenberg's uncertainty principle, they do not commute, which means that we cannot measure the eigenstates of a position and momentum operator at the same time. So after covering that, the basic background, then he moves to the Schrodinger's wave equation, which is the standard workhorse of quantum mechanics, non-relativistic quantum mechanics. And then he gives examples where quantum mechanics is applied, or it was applied in the beginning, the very first applications of quantum mechanics. So he shows how to solve the problem of electron in a quantum well and quantum tunneling, and the problem of quantum mechanics applied to hydrogen atom. So he covers all that, and then he moves to the next stage where when one cannot completely solve exactly any problem because of the complexity of the problem's nature, so one has to use some approximate methods, and the most common of these are variational methods and perturbation theory. So let me talk a little bit about what these approximation methods are. So let's say you can apply quantum mechanics to hydrogen atom, which has only one electron, and you can calculate the quantum ground states of hydrogen atom completely and accurately using non-relativistic Schrodinger's wave equation. But when it comes to the next atom in the periodic table, which is the helium atom, which has 2 electrons, the exact methods cannot apply. It's mathematically impossible to exactly solve the helium atom and to find the quantum eigenstates of a helium atom. So one can do then the next best thing, which is to come up with some sort of approximation. And that approximate method is known as variational method. So using variational method, one takes the the standard reference, which in this case is the hydrogen atom, because we know the quantum ground state of hydrogen atom, which can be calculated. And using that as the standard reference, one then approximates the value of the quantum ground state of helium atom. So this is what this variational method is. And then there are other variational methods which are known as perturbation theory. So perturbation theory comes in 2 different flavors. One is time independent perturbation theory and other is time dependent perturbation theory. So let's take them one by one. Let's say you are interested in a problem like you have a hydrogen atom and you apply a strong electric or magnetic field to it, a static electric field or static magnetic field. So in case of static electric field, the effect is known as Stark effect. It changes the quantum eigenstates of hydrogen atom. And one would like to, because these can be actually observed experimentally, so you want to be able to calculate them theoretically. So to calculate the Stark effect, you use time-independent perturbation theory. And in the second case, where you apply a static magnetic field, this process, this effect in physics is known as Zeeman effect. What it does, it basically changes the quantum eigenstates once again, but in this case, the application of magnetic field lifts the degeneracy in the eigenstates. So for example, if there were previously two eigenstates which were basically at the same energy level, so you can see this is one eigenstate, this is another, and they are at the same level, so they have the same energy. So applying that magnetic field just shifts one over the other. So now there is a finite gap in energy. So this can also be calculated using the time independent perturbation theory. So these are also, these perturbation theory is a approximate effect, and so one can calculate very good values using these the perturbation theory. In the third case, there is a time dependent perturbation theory, which is basically you are applying. So basically, in the first case, we said static electric field and static magnetic field. So let's say in this case, you're applying an external influence which is time dependent. Let's say you shine light on an atom. So this time, because light is a transient phenomenon, it depends on time. So now you need to use time dependent perturbation theory. And so all this is covered in beautiful, clear detail by Messier in this classic book. So after covering all these, then Messier moves to very high level subjects like collision theory. So where you are interested in collision of atoms with each other and how you use these perturbation theory methods to calculate the scattering cross section. So let's say you have atom coming from here, atom coming from here, and after scattering, they're going in two different directions, multiple directions. So you want to be able to calculate the cross section, which tells you what's the probability of an atom going this way or this way. So he covers that, and after that, then he talks about the relativistic quantum mechanics, which is a Dirac's equation. So non-relativistic quantum mechanics, the workhorse is Schrodinger's wave equation. For relativistic quantum mechanics, the workhorse is Dirac's equation. So what is relativistic quantum mechanics? It's the quantum mechanics plus Einstein's special theory of relativity. So for example, even in an atom, in the ground state of hydrogen atom, the electron is moving at a very high speed. So its speed is like a few percent of the speed of light, which means that one has to take into account relativistic effects which come into picture once a body approaches the speed of light. So this is Einstein's special theory of relativity. So Dirac, really a genius physicist, I've talked about him in my review of his book a few months back. So he came up with this theory which combines quantum mechanics and special theory of relativity. And so then that's the theory one applies. One, when a quantum object like an electron is also moving at a very high speed, close to the speed of light, and so that equation is known as Dirac's equation, and Messier talks about that in great detail, where that equation comes from, how one solves it in cases one is interested, and how to interpret the solutions. And of course, that brings so many wonderful ideas like antimatter. So Dirac's equation predicts the existence of antimatter. So even though the equation was proposed just to handle the behavior of a quantum particle which has a velocity which is a significant fraction of the speed of light. But once you solve this equation, it gives solutions which basically, apart from describing the behavior of electron, also gives you information about the antimatter particle for electron, which is a positron. So positron is an antimatter partner for electron. So that Dirac equation does that. Okay. So after talking about Dirac's equation, he moves to some really high level topics, like where one talks about quantum electrodynamics and quantum and the quantization of the Maxwell's equation. So basically what, and I've talked about this in my previous reviews of my books, of these great books on quantum field theory, like Peskin and Schroeder and Schwartz. So there one has to deal with the fact that you're dealing with uh, relativist, an electron which is moving at a relativistic velocity, and you're also dealing with electromagnetic fields which always move at the speed of light. So one has to do what's known as a second quantization of electrons wave theory, which is the Dirac equation, and you have to take the Maxwell's equation and you have to quantize it. So this is where one moves into the realm of quantum field theory. So that's what I meant, like the really advanced topics for a book on quantum mechanics is where you approach quantum field theory, and that's where Messier stops. So because then you have to go to the books on quantum field theory. So he sets up the stage, taking you all the way to the quantum field theory. So this book is Quantum Particle Mechanics. It covers non-relativistic and relativistic quantum particle mechanics, and then it sets the stage for somebody who's interested in quantum field theory to go to these advanced subjects. So this, I hope you enjoyed this lecture, and if you have any questions, please put them in the comment box below, and I hope to see you again in my next lecture. Okay, take care. Thank you.